Friends, welcome to this video on displacement coefficient method. In the same video also the displacement modification method and equivalent linearization method have been explained. I want to remind you one thing, that for understanding any current video you need to have the knowledge of the previous videos put on this channel. So please watch the previous videos so that it is clear to understand the current video. Target displacement, we are going to find what is this. We have understood this in the previous video, that it is the displacement at the performance point of the system. What is performance point? It is the point where the reduced demand and the capacity curve intersect, so that it becomes the unique point where the capacity of the system and demand imposed on the system are equal, so that it is optimized or economical design. Target displacement is expressed as capital delta T or small delta t, and it is also popularly known as the design displacement, expressed as delta D. Is the displacement at the performance point, also may be noted as delta PP. So for the purpose of design etc., it is expressed in spectral displacement and the unit is meter. For your recapitulation, I have shown here the previous examples we had taken in previous video of the demand curve here, which is 5% damped elastic curve or design spectrum of the code, and due to the damage in the system corresponding to some point, the reduced demand curve is shown here, and the capacity curve is shown by the green curve. They are intersecting at this point, so this is your performance point. The displacement on the x-axis corresponding to this performance point is the delta t, which is your target displacement or the design displacement. There are various ways of finding this target displacement. We shall be discussing this here. One method we have already discussed based on ATC 40, which was capacity spectrum method. So let us see what are the methods available for finding the target displacement or design displacement. Number one is capacity spectrum method, which we have discussed in our previous video. Then you have the displacement coefficient method given in FEMA 356, equivalent linearization method given in FEMA 440 document, and displacement modification method given also in FEMA 440. The displacement modification method given in number 4 is a modification of this second method, displacement coefficient method, which we are going to discuss in this video. Out of this, we have already discussed the capacity spectrum method in the previous video. The target displacement in FEMA 356 in the displacement coefficient method is given as C0, C1, C2, C3 SA T E square G divided by 4 pi square. So actually the displacement is actually this part SA T square by 4 pi square G, and which has been modified by these modifiers, which are the coefficients. That's why it is called coefficient method. Now where from this expression generated, let us see the genesis of the expression. We have the relationship spectral acceleration equal to omega square SD. Omega is the frequency, angular frequency, and SD is the spectral displacement, and we know omega equal to twice pi by t. So putting this, we can find out the value of SD. SD equal to t square divided by 4 pi square SA. Now in the codal design spectrum, you are not given SA, but generally given SA by G ratio. So if you want to use SA, that ordinate you have to multiply it by G so that you get SA. So finally the expression becomes SD equal to t square by 4 pi square SA into G. Now for a purpose, we do not use only t but the effective time period. So that's why the time period here shown is T square, effective time period. So this is the basic expression for the spectral displacement, and this has been modified through the imposition of the coefficients C0, C1, C2 and C3. So let us see what are the coefficients, then you can find out the target displacement delta T. Let us see the coefficients in the nutshell. What are these? So C0 equal to the effect of conversion from S-DOF system to M-DOF system displacement. We are finding displacement, this is a displacement. So if you have a multiple degree of freedom system, you convert it to generally a single degree of freedom system, and what should be the relationship between their displacements at the top of the building is given through the expression C0. C1 is a correlation between the linear displacement and non-linear displacement. Linear displacement you can find easily, and non-linear displacement you have to carry out the non-linear analysis. So doing linear, whether we can reach non-linear, that can be taken care of by the coefficient C1. C2 is the effect of pinch hysteresis and other effects we will see in the next slides. C3 is the coefficient that takes care of the P delta effect in the analysis. So let us see the coefficient C0. C0 is modification factor to relate spectral displacement for an equivalent S-DOF system to the roof displacement of the real building. So equivalent S-DOF system is also known as ES-DOF system. We have a real building here which is 3D building, which is multiple degree of freedom system. So through dynamical equations, it is possible to convert this to a single degree freedom system. So it has a single mass and some effective height, effective stiffness and so on other properties. So that will be called as equivalent single degree of freedom system, ES-DOF system. So this is the real system which has the roof displacement at the top that we want to relate with the converted equivalent single degree of freedom system displacement, and this in spectral displacement unit. Further reading about the C0, C0 can be taken as the first modal participation factor. Participation factor corresponding to the first mode of the system, or you can take the values given in the table here. So the tables are given for number of stories 1 to 5 and then further 10 story onwards. And you can make linear interpolation for in between stories. Now these are given say for shear building and other buildings. What is shear building? A definition is given here: buildings in which for all stories interstory drift decreases with increasing height. However, shear building means a building having rigid diaphragm, rigid beams, so that due to the effect of the rigid diaphragm at the floor level, you have the displacements of the stories in the shear mode, not in the cantilever bending mode. A building is actually a cantilever system, so it should have shown a cantilever mode, but it will not show in these cases. The case is when there is rigid floors and beams in the floor levels, then it will show shear bendings mode. This was discussed in earlier video. Triangular load pattern nobody uses. For this coefficients are given. Uniform load, you remember, uniform load we have used for push-by analysis. Other loads are not given, so it is not clear what you will take for other loads. Other than shear buildings, for any load pattern, you can take these values. Now let us see the coefficient C1. C1 is modification factor to relate expected maximum inelastic displacements to displacement calculated for linear elastic response. So as we discussed earlier, it is a correlation between the linear displacement and non-linear displacement. How to get the values? It will be equal to 140. It will be equal to 1.0 when the effective time period is greater than or equal to Ts, and equal to given by this expression where the effective time period is less than Ts. Whereas T we have discussed, we shall discuss it further through a diagram, and Ts is called the characteristic time period. This is this time period where your horizontal arm of the design spectrum is meeting the parabolic arm of the design spectrum, that corner. This is also known as corner period or the characteristic period. So T is effective fundamental period of the building, T is a characteristic period, R is called the strength ratio. What is the strength ratio? We shall see through mathematical expression also. Strength demand calculated to yield strength coefficient calculated by equation given in the documents. This document is we are talking about is the FEMA 356 document. So the strength ratio R is given by this expression SA divided by By divided by W into Cm. Actually, strength ratio is equal to elastic demand of the system, which is equal to SAW, and the ratio of this elastic demand to the yield based shear of the system, which is By. By is obtained through bilinearization of the capacity curve that we have discussed in previous video, and this whole expression is modified through a modifier Cm. What is the Cm is given here. Depending on the number of stories 1 to 2, 3 or more, concrete moment resisting frame, concrete shear wall and other conditions, and steel moment resisting frame and other conditions are given here. So most of the cases it is 1.0 and in other cases also very near to 1. Cut and start. Now let us see what is this effective time period. We discussed in earlier video the bilinearization of the pushover curve. So here is a pushover curve which has been bilinearized with respect to target displacement. So you have to know this point in the beginning, or you can assume the point in the beginning and then extend the curve backward like this, and from the initial tangent to the capacity curve draw another line which is dotted here, and they meet at certain point. This point is your yield point. As a consensus, this is declared as a yield point, and the corresponding base shear to this point is the yield base shear, and the base shear corresponding to the target displacement is the Vt, target base shear, and you have a point here at level 0.6 By. So if you take a point 0.6 By and consider the point By and consider that this area here which is above this dotted line and the area of the triangle here below the dotted line, if these are equal, then your yield point is achieved at this point, which we have discussed in previous video. Now look at the gradient of the dotted line. The gradient of the initial tangent to the capacity curve is Ki, which is the stiffness, so Ki, and the gradient of the dotted line which gives you the yield point is K effective Ke. So with respect to Ke, you can define as you can see in this expression, you can define the effective time period. So effective time period equal to Ti initial time period into Ki initial stiffness divided by Ke, the effective stiffness of the dotted line here. So effective time period is meant here, this bilinearization gradient of the line from the origin. Now this is the case when the post yield slope is positive, that is, it is increasing gradually. The capacity curve is increasing so that all the stiffnesses will be positive. But in certain cases the pinched capacity curve can be obtained where it is falling gradually. So it is indicating that the base shear is decreasing or strength is decreasing gradually with deformation in the system. So in this case the stiffness is set to a negative and the bilinearization is discussed here in this way. So we have understood this is not a typical case, it can come in certain special cases only. So we have understood how to use the value of Te. Now let us see the modification factor C2. C2 is the modification factor to represent the effect of pinched hysteresis shape, stiffness degradation and strength deterioration on maximum displacement response. Pinched hysteresis means the hysteresis curve is not smooth but it is having kinks in some places. C2 is given in this table for different kinds of performance levels of the structure: immediate occupancy, life safety and collapse prevention. and based on this time period less than or equal to 0.1 second or greater than the characteristics time period. And for framing building type 1, type 2 as explained in the document of FEMA 356. For the time period in between 0.1 and TS, you can interpolate the values. So this C2 that takes into care the effect of pinch hysteresis, stiffness degradation and strength deterioration during the progress of the capacity analysis. C3 is another factor, is the modification factor to represent increased displacement due to P delta effect. P delta effect we have discussed in previous video. This increases the displacement and is detrimental to the structure. More P delta effect means there is more danger of collapse. So C3 is given by this expression where alpha equal to the ratio of push till stiffness to effective stiffness. Now what is this? After the yield point you have seen the stiffness is reduced, it has a inclination, the line inclined at lower angle now. So push till stiffness is now lower than the initial stiffness. If you take ratio of the push till stiffness to the initial stiffness, that is stiffness after yield and stiffness before yield, then you get the ratio alpha. And the strength ratio used here, we have already discussed earlier, here again shown by the expression. Cm is the effective mass factor given in table 3.1. Alternatively, Cm can be taken as the effective model mass calculated for the fundamental time period. Though it was written as a model in the document, it is actually a model. So I have given a correction here. The table 3.1 is shown here, which gives you the value of Cm based on the number of stories. But this we have discussed in the previous slide also. Now let us see the next method, displacement modification method. This is the modification carried out over the FEMA 356 displacement coefficient method, and it is presented in FEMA 440 document. All these documents I am mentioning are freely downloadable. You can download and go to the source and read further. So target displacement was given by this expression in the modified displacement coefficient method in FEMA 440. See that C3 has been removed and they have given the value C1 and C2, and this expression they have not given. I have assumed this is the expression because they have not mentioned anything regarding C0, whether it is discarded or it is taken. So I assume it is taken, and the coefficients are now C0, C1 and C2 only. And the values of C1 and C2 have been changed in FEMA 440 document. So C1 is given by this expression, which involves the strength ratio and a new factor A here. So what is A? For soil class B it is 130, for soil class C it is 90, and for soil class D it is 60. For time less than 0.2 second, use the value of C1 corresponding to the value of 0.2 second. That is, if you put here 0.2 second, you get a value which you can say as C1 0.2. For time greater than 1 second, use C1 equal to 1.0. So it is flat after 1 second period. C2 expression in this original target displacement is given by this new expression in FEMA 440, which involves the strength ratio and time period. Here again confusion, this time period, whether it is Ti or T, is not mentioned. And again, for time less than 0.2 second, use C2 value for 0.2 second. For time greater than 0.7 second, use C2 equal to 1.0. And in between you can allow interpolation. So this gives C2. So all the expressions are known. C0 will be the same as given in FEMA 356 displacement coefficient method. That is what I am assuming, because this expression is not mentioned particularly in FEMA 440. They have categorically said that C3 has been removed, C1, C2 have been changed, and silent about C0. Now in FEMA 440, another method is given, which is called Equivalent Linearization Method. So it is a bit complicated. The procedural steps from FEMA 440 I have taken up here, and Just we are mentioning this. So select the spectral displacement representation of the ground motion with an initial damping beta naught. That is, it is telling about the design spectrum at 5% elastic damped condition. Then modify the selected spectrum as appropriate for soil structure interaction. This we have not discussed so far in the video. With soil structure interaction, your structural response changes, also ground motion may change, so that modification is done here. Convert the selected spectrum modified for SSI when appropriate to an acceleration displacement response spectrum format, that is ADRS format, which we have discussed in previous videos. Generate a capacity curve for the structure to be analyzed. Select an initial performance point, which is named as DPI API. DPI is the spectral displacement at that point, and API is the spectral acceleration at that point. So this is a assumed target performance point. Develop a bilinear representation of the capacity curve that we know how to do. For the bilinear representation developed in step 6, calculate the values of post-elastic stiffness alpha. This is very easy. We have said after yield the stiffness of the curve, and before yield the stiffness of the curve. If you take the ratio of these two, you get alpha, and ductility is mu, which is given as below. Alpha can be expressed also in terms of the ordinates of the performance point and yield point. So this is like this. Alpha is the post-yield stiffness ratio, can be given through this expression, and ductility is the maximum displacement by yield displacement, so it is dpi by dy for the performance point considered. Step 8, using the calculated values for the post-elastic stiffness alpha and ductility mu in step 7, calculate the corresponding effective damping beta effective. Similarly, calculate the corresponding effective time period T effective. That is, beta effective we have expressed in previous videos as xi E, effective damping, and T effective is nothing but Te, which is taken up here also. So how to get this beta effective damping? When the range of the mu is within this 1 less than mu less than 4, then beta effective is given by this expression. Beta naught is the material damping, which is 5% for concrete and 2% for steel. For other range of ductility, 4 less than or equal to mu less than or equal to 6.5, beta effective is given by a new expression. Furthermore, if 1 less than mu less than 4, then the effective time period is given through this expression. T naught is initial time period when it was elastic. Then for other range of the ductility is given by another expression, and when mu is greater than 6.5, T effective time period is given through this expression. So this involves only ductility and the initial time period. Step 9, using the effective damping, that is beta effective, from step 8, adjust the initial ADRS to beta effective, that is find the reduced demand curve. Determine the estimated maximum displacement di using the intersection of the radial effective period T effective with the ADRS for beta effective. We discussed in previous video that radial lines from the origin in the ADRS format of the capacity curve or design spectrum curve gives you constant time period. So since time period T effective you already calculated, you are in a position to get that line, and wherever this line is intersecting the capacity curve is your performance point. So you know the di ai point here. This is first trial point, of course. 11th step, compare the estimated maximum displacement di with the initial value which was written as dpi. If the performance point is close to each other, then you can stop or you can further carry on iteration. We have discussed this in previous video also. So the different methods, we are concluding this video here. Different methods for finding target displacement or design displacement or locating the performance point which is the ideal point for design, are given through these four methods. Of this, the capacity spectrum method was discussed in another video. Displacement coefficient method we have discussed in current video, and also we have discussed on equivalent linearization method and displacement modification method in this video itself.